remotely?
Yeah.
Joe, can you hear me remotely, Joe?
I can. Hello.
Okay. Whatever. Yeah. Well, good morning to all of our external collaborators, partners remotely, as well as our faculty members, and also to all the students here we have with us here today and the art staff member. Welcome to the first live seminar that ARCS holds every 2 weeks. And the purpose of this seminar is to provide an opportunity for our student fellows who we are training to be, if you don't mind, can I take a moment?
That's fine.
Who we are training to be a convergent research leader. That is, our student will be leaders taking leadership role in a convergent research project that involves professor, student, and collaborator across multiple disciplines. So it's really important to have a mechanism for our student to talk about what they do, but honestly, to provide them opportunity to enhance their technical presentation skill. And as leaders, you need to present your work, and this is a great opportunity for you all to do that. And there's no better place to do it than in front of a very friendly and warm audience, followed by food and drinks. So lots of motivation, right? And there's going to be lots of good feedback from our audience as well. In today's talk, we're going to have two presentations. The first one is the AI assisted knowledge graph design for cadre robots that I and Dr. Lee supervise this project. We also have a number of collaborators, and can I just ask them to just quickly say hello from where they are? And Richard Otis, Richard, are you there, Richard?
I believe we just heard Fab and Daniel Grande.
Daniel, you there?
Hey everyone,
Hey, Daniel.
Hello.
nice to see everyone in person.
Who else do we have from externally?
Fabiola is here as well.
Fab, you there, Fab? Could you say hello?
Hi, everyone. Joining from Indiana. How are you? I'm from
Yeah.
Autodesk, just in case. I forgot to mention that.
Yeah, Danny and Fab are from Autodesk. Do we have Thomas or Richard or Mitch on, sir? Okay. Well, on behalf of art staff and student, again, very grateful for the sponsorship of Autodesk in this project, but also I think really is the mentorship of our students, Danny and Fab. They're just phenomenal educators at heart, right? Even though at Autodesk, and I really admire them for their commitment and passion to the next generation of students, and the time they put into students is just phenomenal. And I really have to make sure we acknowledge that and make sure our students appreciate what they do for us. So with that, I will turn it over to the student presenter today, Elliott. He's a fellow, and he's going to be talking about his project. Are there other student presenting, Elliott, or just you?
No, it's just me.
Okay, it's just going to be Elliott presenting, and then for 20 minutes or so, right?
Yeah.
And we're going to have like about 10 minutes segment for our audience to ask questions, and Elliott and from students, you're welcome to ask questions as well. So please give me a warm welcome to Elliott and his team.
So thank you. So I'm here today with the AI knowledge graph design for the cadre robot. Can you guys see the screen? Perfect. So as you can see, we do have a number of collaborators working with our group. From JPL, we have Dr. Richard Otis, Dr. Thomas Liu, and Dr. Michael Ingham. Unfortunately, they couldn't be here today, but they're generally at our other meetings. From Autodesk, we have Daniel Grande, Daniel Noviello, Diane Galtz, Fabiola Clayton, and Kaveh Hassani. They couldn't be here, unfortunately. So just Daniel Grande and Fabiola could be there. And we're also working with Dr. Vincent Fierro at the NIST, the National Institute for Standards and Testing. He's been helping us do some of the functional definition work. So basically, the project description Autodesk is investigating methods for improving the design of assemblies by learning best practices from previous designs, encoding this data in a knowledge graph, and then assisting the designer during the detailed design process. Using a comprehensive collection of the real-world CAD data, as well as involving user research to identify what design knowledge we need to capture, a method to derive insights from the various data sets is being developed. And the applicable insights are to be used for a case study involving a redesign of NASA's cooperative, autonomous, distributed robotic explorers, otherwise known as the CAD. So in order to accomplish this, we have a few different ways of doing this. So one of the first ways is going to be human-centered studies. And this will help us figure out what design knowledge we're going to need to capture for the engineer. How would a design interact with and trust a design knowledge system? Because this is basically putting your design into an AI's hands. How could a designer provide feedback to correct the system? And then on a more technical centered research, how do we represent design knowledge as a graph? What design knowledge can we extract from CAD? Because some of it might be too nebulous, some might be easy. And how might we visualize the state of the knowledge graph to permit auditing, debugging, and improvement over time? Because we want this to be scalable. So by representing design knowledge as a graph and enabling automated reasoning, we can build a single scalable knowledge graph from multimodal data sources. And this is capable of powering a new class of intelligent tools for designers and engineers. Further, with this base in the transition from knowledge as an abstract into a programmable medium, such advancements as AI-assisted design or smart self-repair of remote machines are furthered. So some background on the project. In product design, efforts to consolidate design knowledge in knowledge graphs have resulted in robust graph representations of domain-specific semantic relationships. Engineering design knowledge graphs have been shown to be useful for concept generation and evaluation. And however, there is an opportunity to expand on prior work towards later phases of the design process by extracting design knowledge from the CAD models to complement existing semantic networks. So in order to achieve our goal of representing knowledge as a graph, we have to establish some types of knowledge. So commonly we have the declarative knowledge, which is knowledge about or answers to WH questions like who, what, where, when, things like that. These are things that you know, they can be backed up, they're easy to figure out. Facts, world, personal history, rules for mathematical operations, these are all known as declarative knowledge. These are easy to express in the form of words and symbols. Procedural knowledge is slightly different. This is something that you know how to do. These are implicit, subconscious muscle memories. When you're driving a car, you're not necessarily thinking about everything you're doing. Some of that is implicit. So how to drive a car, how to throw a boomerang correctly, how to throw a ball. These involve muscle memory, and they're hard to explain verbally. And while declarative knowledge may be relatively easy to quantify graphically, procedural knowledge is more nebulous and difficult to capture graphically. The knowledge may, however, be learned through policy applications, and these would be greatly helped by the support of knowledge graphs, since these types of behavior are inherently learned and inherently teachable. So with the knowledge graph allows us to take information connected in a way that's useful for analysis. In this graph right here, we have a representation of Paris, and this is what's called a semantic triple. So we have a subject, a predicate, and an object. So for example, the Eiffel Tower is located in Paris, or the Louvre is a museum. When all semantic triples of an arbitrary domain are connected, a knowledge graph is formed. So extending this, using this concept of the graphical representations of nodes and blades, a reasoning engine such as an AI can make inference that were not originally included in the set. So by combining multiple data sets that have been set up in a consistent manner, new previously unknown and unshown graph information may be found. So you can see over here, when a new information piece is introduced, say that Paris is part of France, the AI can then take that simple information and extract it to a number of different things. They can then determine that the Eiffel Tower is in fact in France through inference. So it's the potential applications for knowledge systems is pretty numerous. So we could retrieve existing components from databases and then ask the system, what are suitable material choices for this bracket given design requirements? This is a really common question to ask design engineers. which O-ring would be suitable given an X tolerance and a Y tolerance. These are things we go through all the time as design engineers. Fastening method would minimize weight. Weight is always a huge thing. So if we can have a graph actually go through and minimize and figure out what the best weight is, that would be really helpful. Parameters based on available manufacturing. One of the biggest design challenges we have as design engineers is I can make a part, but how do we actually physically make it? So having an AI monitor this sort of thing would be able to look at your design and say, that's not machinable, that needs to be 3D printed, things of that nature. Predicting principal failure modes, this is already something that we're doing with finite element analysis, but that's a passive system. You have to go in and set everything and then let the system do its thing and then interpret the results. An AI could do that on the fly without you having to set everything. And learning best practices from previous designs. Looking at previous designs and then analyzing them, the computer should be able to start to find best practices, diameters and things that would be standardized. And given, say, a plastic material, it would be able to find the distances that the holes would have to be to prevent catastrophic failure, things like that. So we are working in partnership with Autodesk, and we're using the Fusion 360 data set. This is a robust data set that gives us access to a lot of CAD stuff. So we're not just, designing some things here or there. We're using an existing database that's been established by a fairly large company. So we'll go a little bit into knowledge graph-based AI learning systems. So in order to begin the task of teaching an AI to use CAD data to make these suggestions, we need to transform CAD models into graphical representations. This means loosely, we need to represent the mechanical parts as nodes and the relationships between them in the assembly as edges. So as you can see here, the representation of a CAD assembly as a general knowledge graph can be done through many lenses. You can see on the left, we have the assembly data for just a small part of the overall assembly. And in the middle, we have various ways that we could establish a data set for this. We could look at the assembly tree and look at the physical representations and the physical actual parent-child relationships. We could also look at the individual joint relationships for each part versus the parent-child relationship, because a part might be attached to another part, but it might be functioning and interacting with a third or fourth part. So we can also do contacts, which is another method of joints. So you can have joints that may not have complete contact, or we can have contact on different surfaces or different edges. And we do have parametric dependencies. If the design has been done professionally through parametric means, we can actually use the existing relations between the parts to figure out what the other parts are doing. And you can see all the way on the right, the interaction between all of the different functions when you're designing and creating a part, they may seem interdependent, but they're not. They're all intrinsically tied to each other. So this in turn drives the design function and the design process. So for our actual framework, our initial research began using the Oregon State Design Repository, which was conveniently arrayed in a way that's conductive to representation by knowledge graph. It's a loosely based system that has a whole bunch of different assemblies, but the assemblies are linked based on energy flows and other things that aren't necessarily design-wise. So while the initial framework was useful for us, the overall framework isn't useful for our application. But we use the same sort of idea. So when we have a knowledge graph, like in the OSR, they have the edges, which would be the connections between the nodes. And these right here show child-parent relationships. There's no features or anything. For the input flow, we have the source in and input flows. These are mainly energy flows, which is really hard to track. So output flows, same thing with the energy flows. So instead of this, we're now focusing on the Fusion 360 design database, and it's a much more robust framework, and we can connect many more aspects. So you can see for us, the definition of edges, which are the connections, which are links in the graphical bodies between the joints and contacts. We've also been looking at possibly doing some other joint and contact surfaces there as well. Additional features such as weight geometry, finite element analysis, et cetera, those could be considered as well. So for each part in an assembly, we established numerous nodes and connected these by edges. Features deemed important were added to the database, such as semantic names and geometry. these were established as nodes, and then the graph is populated with blades consisting of parent-child relationships. So as you can see here, we have, say, a bolt, very simple assembly, a bolt and a nut, two parts. So we have body one, and this shows the semantic name. You screw, the material is steel, satin steel. Physical properties, we have the area, the volume, the polygon mesh, which shows the geometry, and all the global features. And then we have the same thing for the second body, which holds. And this right here, when you look over on the other side for the edges, we have the parent-child relationship, shared components, and then the shared parent components. So this way you can see from the right, these two bolts are actually not just connected in one or two different ways, they're connected in various ways. And this is one of the most simple assemblies that we can actually use. So initial trials of these sort of systems were promising, but they had some issues. So we were attempting to suggest a material for a part based on based on known information, and it came back with a little bit of issues. As you can see, we had very few bodies without any errors. So in order to minimize this and actually help ourselves, we decided to look at the confusion that was apparent in the AI. So as you can see on the left, it's not very organized. There's a lot of confusion. And then on the right, once we added some appearance info, the confusion lessened to a manageable point. The system predicted the majority of parts as a nebulous other category. So we found that adding the targeted data increased the accuracy and reduced confusion in the system significantly. For this reason, we chose to develop a system to allow for human input in order to train the system correctly using additional input vectors. So in order to introduce this, we had to start introducing function and flow. So the function of things would be like supporting load, transmitting heat, force, electricity, containing pressure, things of that nature. Constraints, safety, maximum dimensions, things like that. So when considering additional features that may be used to help define and train the system, we decided to focus on functional definitions. This decision was made due to previous research in the field of AI-driven knowledge graphs done by the OSDR and NIST, which is why we have Dr. Ferrero helping us. Because they already had established a list of functional definitions, other databases might be integrated much more easily in the system. So our definition set is organized to have 3 tiers of parent-child relations. The top level functions are branch, control, magnitude, convert, provision, signal, support, channel, and connect. So you can see these can go in a lot of different directions. The function list is as complete as we can make it, which means probably 70% of it isn't actually applicable to what we're doing now, but it will be applicable later when the thing is scaled up. So before we can begin manual labeling, we needed to filter out an assembly that are not viable for study due to a number of mitigating factors. As you can see, once we actually went and eliminated everything, we ended up with about 221 bodies, which brought us from 56,000 things that needed to be labeled down to 7,400, much more manageable. So in addition, we're doing user research, and this will be done by Max Slade, a graduate student in anthropology. He'll be doing interviews with JPL staff and engineers. We'll be using this to determine what the best course of action is, what are the important things we need to find, all of that stuff. Additionally, we'll be able to find other aspects of research for other ARCS things, like the Open Caesar project will also be doing these interviews and using this information as well. So the preliminary cadre design, this will be done as a case study at some point soon. This is the preliminary design, and it's basically going to be done parametrically and done through the actual ideals that we've established through this part right here. This is actually just preliminary design, doesn't reflect what it's actually going to look like. Additionally,
quickly explain what cadre is to the audience.
so the cadre is the cooperative autonomous research. I explained that over in the beginning. This right here will be a swarm of robots that will be used to supplement the rovers that are already on Mars and will be sent to the moon, and also allow for autonomous exploration. They can communicate via Bluetooth, and they're basically tiny little shoebox robots that'll just be exploring the moon and Mars. This is a part of the experiment that's on schedule for the next few months. So it's not as robust as the rest of it. Additionally, we have entered into the IDETC, the International Design Engineering Technical Conference. We have submitted a paper. We are waiting on submission right now or on approval. These are the principal authors. And this work is very comprehensive as far as what we've been doing. It goes over methodology as well as everything itself. I do have some quotes here, so if you guys want to see the actual quotes, I can link this later. But for time's sake, I won't go over those. The paper itself just nutshells everything that I just did. It has some additional experiments, so if you're interested, you can go ahead and read that. We can give that to you. So for the next steps, we'll just be going through the human interaction. We're going to be discovering additional avenues of knowledge graph building and input from engineers at JPL, complete redesign of the cadre, and then we'll expand the usability of the system to include suggestions in addition to material. We'll also be establishing a standardized function definition list with the help of this. So. Any questions?
Yes, we'll now have 10 minutes of Q&A for Elliott.
Yes.
Elliott, I think it was a question to you.
Can you read the question from earlier?
Why are they needed? That's all I got. That's why is what needed.
Maybe where is, what school is that from?
For Samira,
Samira,
Yeah,
you asked
I guess that is my central question here. I can't gauge through this presentation like what the need is, why this effort is being put into creating this. I mean, because I'm not in this world, so I don't understand. If you could explain that to me.
so to kind of give an overview, right now, design tools such as Autodesk, Fusion, SolidWorks, CATIA, these are what's known as passive tools. They can only do what you tell them. It's like a hammer. If you have a hammer and you put it on the table, it's never going to hammer a nail until you pick it up and physically make it hammer that nail. So design programs are very much the same way. It'll do whatever you tell it. If you tell it to do the wrong thing, it will absolutely do the wrong thing. It doesn't care. So the goal of design in the future is to create systems that aren't passive anymore. They're active. They'll be able to actively scan all known information and all things that you as an engineer would have to spend decades learning. And it'll be able to parse that very quickly and then apply it to what you're doing. So instead of it allowing you to make a part that doesn't work, it will actually come out and say, hey, this part's too small, this part's too thin, this part needs to be a better material, things like that. In addition to that, knowing manufacturing methods when you're doing design is incredibly important, but keeping up on all manufacturing methods at all times and what can be done and what can't be done, as well as prices of material, that can be incredibly daunting. And if you miss something, that can cost your company millions of dollars. So having an AI being able to monitor this sort of thing and actually provide feedback in real time is incredibly important for designers. It's a thing we're doing anyway. So just having the AI assist, right, will save hundreds and hundreds of thousands of man hours in the next few years.
Ali, can you talk about what it's like to work in a very multidisciplinary team? You know, in this team you have computer science scientists, JPL, AI, system engineering, mechanical engineer, you have manufacturing, you got anthropology,
Yes.
you got design, you got, you know,
Yeah,
can you talk about?
from all sorts of disciplines. I'm a mechanical engineer with the background, like I said, mechanical engineer, manufacturing. I'm also doing my master's in manufacturing systems engineering. So computer programming and stuff, I have no idea. You know, I managed to get through those classes by the seat of my pants. So a lot of the stuff that Brandon is doing with the programming is brilliant, and I don't understand the details of it. But that's a lot of the things that you work with on these multidisciplinary projects. I'm learning a lot about computer programming and things of that nature. I'm by no means able to program any of this stuff, but being exposed to it and watching Brandon go through what he's doing and the challenges he's facing, watching Max go through the challenges he's facing with the interviews, it really gives you a sense of what other disciplines are dealing with, and it very much helps me tailor how I'm interacting with the different group members. Because my mechanical engineers, I can go into nuts and bolts, and my computer programmer, we can talk about computer problems, and anthropology, we can talk about the human aspect. And they're all getting a little bit of that experience too. So it's just a wonderful experience. It really is.
That kind of clarified it, but I was just gonna ask for some clarification on the connection between like the nodal systems that are being developed and the physical aspects of the robots. Which that kind of.
Make sure the remote oriented computer question. After you repeat it.
Yeah. So the question would be, what's the connection between the nodes and the blades and then the physical aspects of the CAD model itself? That in and of itself is most of the is how do we take this physical model and then turn it into just a graph? Yeah. Because the idea is we've got all of this nebulous design knowledge that takes years and years and years to figure out, and you've got to do this, you've got to do that. You can't just look it up or know it. So the question is, can we take that knowledge and put it into a graph that then you can just cross-reference some other time? And the thing that we're finding is, yes, absolutely. As long as it's connected correctly and things are labeled correctly, you can. We also are having a problem a bit on the other side where we have overfitting of data. So you can take your data and make it so perfect that it's essentially not useful. So this in and of itself is the purpose of the experiment. The cadre aspect, that's a case study. That's the thing we're doing. It's other aspects that we're doing among ARCS research, so it makes sense to do a case study on it. But the experiment itself is really on that AI and that design thing itself. So thank you.
So you mentioned that we need Oregon State design report with the for the AI, and what is that report that you about what the can be used for training?
The question was about how we use the OSDR for training. The system itself, we didn't actually use it for training. We used it originally for the framework for setting up the functional basis and taking some of that nebulous design knowledge and converting it into a graphical neural network. They'd already done the problem with their work was it didn't have any geometric data, it didn't have any design data, it didn't have any assembly data. It was just, here's a toy plane, the propeller is connected to this part, but it didn't have the physical stuff. So the things that we needed, we couldn't get. But the framework using nodes and the blades, that's what we actually use. Let's see. So we have. So Daniel answered, isn't it true that human input in AI tech has had ethical problems? What is the team planning in order to mitigate that? As Daniel didn't answer. So mitigating that, so feeding data to an AI can have some ethical issues because the data can be skewed. In the case that we're doing, most of what we're doing is knowledge that isn't opinion. It's just fact. So by connecting these factual things to different nodes, there shouldn't be many problems with ethical issues. One of the issues we are having actually is defining things functionally from a design standpoint can go in many different directions. I can take any part and I can assign many different functions to it. So having a human baseline where different people are doing different labeling, we can have the same person correctly do different functions to the same part because their logic is sound. So we've had to narrow it down to things like only functions that have to do with support in an assembly, or only functions that have to do with energy transfer, things like that. So by restricting the set that we're using, we're hoping to kind of mitigate any of that ethical issue. I hope that answered your question. Any other questions?
All right. Well, Thank you so much, Elliott, for kicking off
Thank you.
the great meeting. It's a wonderful presentation. Can we have the next presenter up here, or is this person present remotely,
Yes.
sir?
No, Jeremy's gonna
Jeremy's
do
right
it.
here.
Makes it a lot easier. I'll talk to you soon, Dr.
And also, this is Dr. Chan. Elliott, that was the most articulate and really great mechanical engineer presentation I've seen. So it's a great job. I'm glad you added your personality to it. So that was a great component to it.
I'm taking a bunch of speech writing classes, so take them, go do public speaking, guys. Trust me.
I don't see.
Yes, yeah.
We have another equally exciting talk titled Europa Sim Human AI Teaming Ethnographic Observation Behavior Trust and Functioning. This is also another really phenomenal research project we have in our program. I think you all hear about the activities going Mars, moons, and all these great mission. Artemis putting the first woman on the moon. So we are all in the thick and thin of it, and Europa is also another exciting project that's going on at JPL that we're involved with. And just like I said before, I'm really grateful to have a really wonderful team of professors, students working on this project. Thomas, I have you here, so I guess why don't you introduce the collaborators, the scientists at JPL who've been working with us, and have them introduce the student as well, Thomas.
Okay, sounds good. And hey, everybody, I'm Thomas Chan, professor of psychology, if you don't know me, and I've been working with So-Young and Basak on and with Jeremy as on these projects. First, to identify these functions that really make teamwork happen. You know, for these projects on Mars and Europa. And I know So-Young and Basak, they're here. I don't know if you guys want to say anything. No, they're yeah, and it's been just oh, do you see that? Oh,
sorry,
yeah.
I had a trouble unmuting. It was just a couple things. I think or maybe it's more of the summary session, but it's been a really great collaboration. I think we got the results we did not expect. And I think that's because you guys are coming with a very fresh perspective. But I think the results, the reaction that we're getting from the mission operation community and also autonomy design community has been really amazing on this work. So looking forward to our next step.
Yes, I also want to add, I learned so much about what psychology research brings, how psychologists can contribute to our endeavors. It was a pleasure.
And thank you. And I've also grown as a faculty, but I've seen the most growth because I'm like almost 40, so I'm not going to grow that much. But Jeremy is still young, and I told them, like, I wish there was a before and after. You know how they have a weight loss, before and after, like Jeremy in terms of like confidence. It was just amazing for So-Young, Basak, and also Scott just to really like facilitate that. So just excited about this work. And Jeremy's wearing a tie too now. See, he's all grown up. He was wearing a hoodie and all that stuff. So yeah, I just want to hand it to him just to talk about what we're up to, and then like some of the directions.
Okay. Hello, everyone. Hello, everyone.
Thank you, Thomas. Thank you, Basak. Thank you, So-Young. Go ahead.
Okay. Hello, everyone. My name is Jeremy. Thank you so much, Dr. Chan, for introducing me. Thank you so much to our JPL collaborators for coming in. I very much appreciate it. This work has been like a year in the making, not gonna lie. So thank you so much for coming and seeing me present this. Let me see.
You can move this back to the screen.
Yes. Let me move this back really quick. Oh.
It's already on the presentation.
Okay. Share. Cool. Okay. Cool. Where's that? Okay. Cool. So
Can people remotely see the screen?
can everyone see the screen?
Yes.
There we go. Cool. Okay, so my name is Jeremy. I just want to thank my colleagues and even JPL collaborators for showing up and being here. This was a year of work in the making, and our work was on an observation for the Europa Sim. So we'll get right into what we're going to be presenting today. So I'll be giving a quick introduction to the Europa Sim and what it's about. We'll talk about our objective for the sim, and then we'll look over our previous publication that we did in October to kind of give you an idea of what we're looking for with the observation. And then we'll show you how we conducted the observation. Then lastly, with the results and some future considerations. So let's get into it. So the Europa Sim, there is a possibility of a lander being sent to Europa, which is Jupiter's moon. And it actually looks like this. And apparently there's ice on top of the surface, apparently, but we don't know. So apparently in 2038, there's a possibility of a lander being sent to Europa. There is one problem where Europa is so far and the day cycles are so different from Earth. There's a huge period of time where there's connection loss between the lander and Earth. So because of that, the proposal is to put onboard autonomy so that while there's no connection between Earth and Europa, the lander itself can make decisions while Earth is trying to get that connection to the lander. And once Earth does connect to Europa, then the teams on Earth can reevaluate the plan that the autonomy made and see if something should be changed or not be changed. So the whole point of the sim was to grab people from the current mission, which is like the Mars rover 2020, grab the scientists, engineers, operations, and put them into the simulation to see how they would work with autonomy. So whether there'd be a good like team dynamic and stuff like that. So, and it was actually really cool because the simulation, all the JPL personnel took it really seriously. So it was just a win for everyone because they were having fun looking at the data, and we were getting some really good realistic ideas of what the team dynamics would be with the autonomy and the JPL personnel. So that was the whole purpose of the Europa Sim. Our objective was to see how science intent was communicated through the planning and negotiation process of the Europa Sim. So now I'm going to try to elaborate what science intent is. So this is our paper that we did. It is Human-Computer Interaction Globe, examining operational trust and tension towards Mars autonomous systems. So these are functions. So through a bunch of interviews that we did with the Mars 2020 personnel, JPL personnel, we found 3 overall, you think about them as like themes throughout the interviews. So the 3 overall themes are corporate knowledge gluer, bridge builder, and efficiency optimizer. And then we also found 14 what we call operationalized functions, which are starting from information clarifier all the way down to ops function. So these functions are our main purpose of doing the observation. We want to see if we can try to identify any of these functions while the planning and negotiation process is happening in the Europa Sim. But we'll go over what some of these mean. So first we'll look at what we call the function labels. The first one is corporate knowledge gluer, fills in any mission relevant knowledge gaps to update rotating missing personnel. And then we have bridge builder, which is conduit to foster collective understanding between science and engineering teams. And then lastly, we have efficiency optimizer, streamlines the task and attention to teams to meet mission deadlines. And we'll get one example of the operationalized functions. So we'll start off with information clarifier. Information clarifier strengthens understandings of objectives and clears up any misunderstandings during negotiations. And then that's a quote from the Europa Sim. I want to clarify if we want to dig in depth or would we dig and surface time. So these are the types of functions that we're looking for throughout the sim. And next we'll go to bridge builder, with one of the functions being opinion validator. Validates individuals' opinions to increase their acceptability with consensus decisions. And this is a quote from one of our participants. I am in favor of what GCMS is suggesting from both a science and ops perspective. So bridge builder is kind of like having those two perspectives of science and engineering, but being able to validate their reasonings. And then lastly, we have efficiency optimizer. Function being forest tree jungler, zooms in and out between long-term blueprints and current situations. And this is our quote from this year of the sim. We are focusing too much on the samples. The signal surface should be prioritized as much as the in-depth. So kind of like zooming in and out between the details of the plan. So these are all the functions. Well, there's more, but these are a couple of examples of the functions that we were going to be looking for throughout the whole simulation. And now I will be going over how we did that. So we used air tables, and we were within the observation itself, the call. And anytime we heard a notable quote, we would write that quote down and we would tag it with role, like the role of the participant, the agenda. So the meetings will last from like 9 to 5, and there'd be different parts of the meeting. So we put the agenda on there and like which segment of the meeting it was in, the task that was going on, and then the outcome of it. And then we would mark which function that we thought the quote was identified with and whether it was pertaining to trust or autonomy. So that was one section we were doing during the simulation. Another section we were doing was we had someone keeping track of everyone's time spoken. So we had multiple timers. One of them, if one of the personnel spoke, we would start the timer, and then if someone else started speaking, we'd start another timer. Each one had their own time spoken. So this is what we did throughout the whole simulation. We kept track of notable quotes that were part of the functions that we're trying to identify. And we're also keeping track of the time. And now we'll get into the results. So it was actually, so this is the functions that we identified for all 4 days, just smashed into one. The most was information clarifier, which is the idea of people trying to get the clear details. So that function happened the most throughout all 4 days. The next in line was forest tree jungler, which is like zooming in and out between details. And then the third one would be opinion validator. So these are the top 3 functions that happened the most throughout all 4 days of the simulation. And then we'll go into, we kind of have an in-depth analysis of each day and like how many functions happen per day. So I'll kind of show like the difference between 2 days at least. So day 1, we can see that information clarifier was the most, followed by opinion validator and then constraint highlighter. And then we'll skip over to day 3, where forest tree jungler had the most, followed by information clarifier and then options final. This kind of gives you an idea. I'm not going to go over all of them because there's actually a lot, but this gives you an idea of like how different the data is throughout the days. So next we'll be going into, we were able to find all the functions and then also see where those functions happen. So these are those segments I mentioned earlier, how like throughout the day there's different meetings, like L2P report, SWOT meeting, and science discussion. We're able to see when those functions happen. It kind of gives us more context of, oh, were they doing more constraint highlighter during science discussion or SWOT? So it kind of gives an idea of like what we can look for. Then next, we also tagged some of the quotes with any mentions of autonomy or trust and questioning autonomy. And as you can see, we have plenty of mentions of autonomy, but we have more trust in autonomy versus questioning in autonomy. So we kept track of that throughout the whole simulation. And then this is our results for the time records. So the sim was spread, or the personnel were spread into 2 teams, Team Omega and Team Alpha. And there were people who verbally spoke, and there were some who did not speak at all. I guess at a caveat, we had more observers, so we do have to change this in the future. But for the most part, more than 50% of people spoke throughout the whole meeting. And we were able to categorize the roles of which role spoke the most. So as you can see, for Team Alpha, operations spoke 56% of the time. right following after is science team, then instruments, and then day 3 for team alpha. Operations spoke the most, we're following science, and then instruments as well. And then we'll go over the last part here. So it was actually a little bit different for team omega. Operations spoke the majority, followed by science and then instruments. So we can kind of see the difference between the team dynamics, since there were 2 different teams, and we can see who spoke the most in general. And then I think after this, okay, so now we'll go into future considerations. So just like how we did, just like how we checked if there's mentions in autonomy and trust, now we want to see if we can tag if there's mentions in trust and teaming. So any code that mentions a team and like trusting the team, then we would keep track of that as well. So that's one future consideration we're thinking about. And then we also want to keep track of the chat, because chat, like in they call it the WebEx call, that's a whole nother dimension of communication that they use. So we actually want to keep track of participation in that aspect as well. That's another thing we're thinking about for the simulation. And then we're also thinking about using, like, adding more context for each day. So each day has a different team, and each day has like a different goal. So we kind of want to add that to our data and kind of give us more information. And I think that is it. Yeah, thank you so much for your time and consideration.
We'll now have 10 minutes of Q&A for Jeremy.
Yeah.
So this sampling was taken across 2 days with 2 different teams.
Oh, sorry. Across 4 days.
Okay, sorry.
So the question was the sample taken off for 2 days? And it was actually 4 days of sampling, like observing the full observation or the simulation. Yeah.
Okay. Well,
Yeah.
Can you talk a bit about the simulation environment, who was there, how many people was there?
Oh, yes.
They have no idea what you.
Yes. So there was 40 participants. All of them were scientists, engineers, and operations. And they were basically doing like the planning and negotiation process of deciding like where the lander should move, what like samples it should get. This was all happening within the simulation. So like similar to like how they're making decisions for Mars, like the Mars rover, they were doing that, but for the Europa lander. So there was 40 participants. It was cool. The data was realistic. Someone like fabricated the data, but it was realistic enough for them to be like really excited about like, oh wait, what if we took this sample instead of this sample, stuff like that. So it was cool to be a part of that whole observation to see how operations did everything, stuff like that. Is there any other questions?
No Zoom questions right now.
Yes.
How do you plan on monitoring the chat? Because I know that you're using auto table and tagging. Are you going to use something similar for the chat?
Possibly something similar. Oh, okay. So they wanted to know how we would keep track of the chat. Sorry, how we would keep track of the chat. We kind of thought about tagging it similar to that, or even just like doing message count. Like this person had this many messages, stuff like that. There's some considerations we're thinking of. What happened?
Well, I think I could, let me ask you what, build upon what Nhut was saying, like, how is it to, because you're actually a business major.
Yeah.
How is it to work with just like all these different mindsets and different like mentalities and backgrounds?
It was very fascinating to come from a different background and be able to try to grasp like the different perspectives. We have the psychology perspective, we have science perspective, operations. So it was really cool to see how all these different perspectives have like their own reasoning and stuff. So it was difficult, but it was really cool to like learn a lot about everyone in general. So it was cool to see all the different perspectives, and even like the JPL collaborators' perspectives as well. So I learned a lot from everyone.
So I do have a question.
Yes.
The thing that we were concerned in the very beginning when we starting off this collaboration is that how can you guys can grasp the operational context, the jargons, you know, what's actually happening in operation or in the meetings, what was discussed. So but you know, we spent a lot of time and I think we got to a really good place, but still I'm really curious for your experience. You know, did you learn some sort of a way to grasp the meta context without understanding the details of the technicality of the conversation?
So what I learned is that JPL itself is very complex. It's insane. I think when we first started our collaboration so young, we really had to learn how operations worked and how all those processes. I remember making that diagram of like who goes to where, like who goes to what meeting. So it was a lot of that helped us kind of figure out the context of like, oh, this is what they're talking about when they're talking about this sampling. But it's a lot of trying to keep up with the conversation, because a lot of times when they're talking about samples, everyone is an expert, which is a good thing, but I feel like that's also a very like complicated thing because everyone could be really like tied into the details. So it's really like kind of like not ignoring that, but looking into that and being like, okay, wait, what's like the main thing that they're trying to focus on? That was one difficulty because a lot of conversations would circle and it'd be like, okay, well, we got to focus, but they're kind of saying the same thing. But for good reason, because all the details and reasoning are like really good, but there is like a better reasoning for everything. So that was very difficult, and we really had to learn how to like shift through the data and kind of just focus on what's important. But yeah, JPL is very complex to say like the slightest bit. I hope that answered your question, but we tried our best.
Sure, no, that's good. Thank you.
Yeah. So I guess you put some of your business background into it, right? You're understanding the organizational structure and the flow of things.
Yeah, 100%. Is there any other questions? Yes.
During the whole interviewing process, did you guys ever thought of recording some of these sessions to kind of keep up with critical jargon going around?
Due to like, okay, so the question was, did we ever think about recording the sessions so that we could keep track of the technical stuff and like that? I guess due to like private information, we can't do that. So yeah, as much as that would help us, yeah, we really have to keep track of what we can do with what we have, basically. That was a good question. I had a question. Yes.
So I heard you come from a business background. You're dabbling in psychology.
Yeah.
But you're also a scientist as an ARCS fellow.
Yes.
So after all of this experience, how would you identify yourself?
It just makes it makes the introduction just more complicated. I guess I would still say a researcher. I would say a researcher at heart for sure, because I still have the business background. I have a little bit of psych background, but I think all of that really funnels into like research. I think that's the one role I identify with the most, I think.
Convergent research.
Yes.
Repeat that again.
Yeah, it would be like convergent research. So kind of grabbing all those different aspects into one. That's what I would work. Thank you for the question.
Yeah, like what type of job would you apply for when you graduate? We're not gonna let you graduate, but what type of job would you, because you're you're getting all these things from the human perspective, the top level, like the top line business stuff, and then also like you're getting the operations part of it. So what type of job would you actually apply for?
I know, right? I don't know. Either I have to like carve one out for myself, or somehow find one that kind of encapsulates all of it. I don't know. That's a very good question.
The wrong response. You have to make your own business.
Thomas, I have to agree with Jeremy's answer that you have to carve out a job for yourself. Honestly, that's it is, right? We have to carve out a center for ourselves because we just believe in what we're doing and how bringing together multiple disciplines and solving these complex problems. So congratulations, Jeremy. Like, you're really gonna carve out a job for yourself.
Yes. Yes.
Until you carve yourself truly gonna be the leader, right? And you defining what needs to be done, have a vision, and create an environment and get people to work with you, right? That's what it comes to. All right, folks. Thank you again. Wonderful. Well, we're gonna end here. Thank you so much for our external audience for being here with us today. And thank you again to the scientists at JPL and Autodesk who mentor our student. I'm very grateful for your participation. And I think this is a great, wonderful kickoff for our fall semester. And I'd definitely love to invite you to our next seminar meeting, which is going to happen in 2 weeks from today, 2 Fridays from today. That's going to be on the 4th of March, right? Yeah. Yeah, we're going to have equally exciting talks, and I hope to see you again soon. And thank you very much.
I thought maybe we could have the students all wave to them.
Oh, yeah, there's
Yeah.
want to have the student wave to
Yeah.
people here and
Yeah.